theorems and remarks. And okay, let's start with examples related to our limit. So during last lecture we have proved the second remarkable limit. So example 1, find limit as x tends to infinity 1 plus k over x power x, where k is a real number. Positive or negative doesn't matter. Okay. So we'll proceed as follows. I'll rewrite it k over x power x as 1 plus k over x power x over k times k. And then if we'll denote k over x as t, right, then we can rewrite our limit using the composition of limits as limit. Okay, if x tends to infinity, then t tends to 0. And in fact, to 0, okay, it depends on the sign of k, right? So t tends to 0 times sigma k. So it means for k positive, t tends to 0 plus, k negative, t tends to 0 minus. And in fact, we should exclude here the case k equals to 0, because for k equals to 0 we cannot use composition theorem, right? So for k equal to 0 we can proceed in a different way. Just in this case we have the limit 1 power x and 1 in an arbitrary, with arbitrary exponent is 1, so that is limit x tends to infinity 1 equals to 1. So so here k is not 0. Then one can rewrite it as 1 plus t power k over t. And now we'll use the limit. So as we know, limit as t tends to 0 doesn't matter with which side we choose. That is a version of the second remarkable limit. We know this, right? So then how we can proceed after that? In fact, rigorously we have several possibilities. Yeah, I'll prefer that one. Here we can use the continuity of the function y to the power k is continuous, right? Is continuous. And what it means? It means that the limit as y tends to y naught y power k equals to y naught power k. Hence, if we'll use the continuity of that function, then we can proceed as follows. So we know the limit exists without any restriction, power k. So we have y power k, y tends to e, hence the limit is e to the power k. E to the power k. Example. Second example, and of course now find the limit. Limit as x tends to infinity, what's equivalent, what is written in your textbook, plus infinity. We have no other. Power x. Right? Yeah. So, if we'll compute the limit in the base of our exponent, right, then we can proceed like 1 plus 1 over x, 2 plus 1 over x, and then the limit of 1 over x is 0, so we have 1/2. Then in your textbook it is written like, oh, I hate this. So like that, right? It's written something like that. Let me, yeah. And I never write it like that. That is completely wrong. I'll explain why. Because, let me write the second remarkable limit. X tends to infinity, 1 plus 1 over x power x. Look, if I write it like that, okay, 1 power infinity, 1 power x, right? And then, 1 power x is 1, right? Yeah, so that is, of course, there is a difference between this writing and that writing, because here it is written infinity, not x, right? That is, so the type of limit 1/2 to power infinity is indeed 0. That's true. But because of that mixing, so if you look at this, 1 power infinity, right? 1 in arbitrary power is 1. So why I insist on the, so it should be forbidden from my point of view. Of course, people can say, oh, it's okay. Indeed, 1/2 in arbitrary power, which tends to infinity, tends to 0. It's true. But if you write it like that, right? So, if you write it like that, then this is certainly wrong. Certainly wrong. I mean, why? this writing is wrong. So this writing is dangerous, this writing is wrong. Why? Because here, when you write like that, what it means? You have a limit in the base, right? You take the limit in the base, 1/2. But you don't take the limit in the exponent. So, it means you have one process. X tends to infinity, right? You cannot do it separately. Like, okay, let us do it in the base, and later we'll do it for the exponent. That is wrong. You should do everything simultaneously. Okay, here it is correct from the point of view that, okay, we know this is 0, right? This type of limits is 0. And we can refer to this type, if you know, right? But more rigorous way is just to use continuity of elementary functions. So write it like that, let's say. Limit as x tends to infinity, e to the power x logarithm x plus 1 to x plus 1. Then what we have? Logarithm. So limit as x tends to infinity of logarithm x plus 1 to x plus 1 is logarithm 1/2. That is a negative number. So here we use continuity of logarithmic function, right? And then what we do? We have then the limit as x tends to infinity of x times logarithm is equal to, so here we have infinity plus infinity, and here we have a negative number, hence that is minus infinity, right? And we know that the limit of exponent is 0. Then, combining those two facts, we have 0. And that is a rigorous way. Okay? So, concerning this writing, I would prefer to avoid it because of that mixing. Yeah. So okay. That is example 2. Next example, in fact, is a version of the second remarkable limit. So example 3. Example 3. Find the limit as x tends to 0, a to the power x minus 1 over x, a greater than 0. Oops. Okay. So, how to proceed in this example? Yeah. Let us consider I will not use. I would prefer to consider another example firstly, but this is considered later, I guess. I don't see that. Oops, I don't see that limit at all. Pity. This version of the second remarkable limit would be considered also. Okay. Okay, let us make the substitution t equals to a to the power x minus 1. Then how it is connected with x? T plus 1 equals to a to the power x, so x equals to logarithm of t plus 1 with base a. Okay, then if x tends to 0, then t tends to 0 as well, because of continuity of the exponential function. So, using the composition theorem, of course, we can do it for a not equals to 1, otherwise a to the power x is precisely 1, hence t is equal to 0, right? So we cannot use the composition theorem for the case a equals to 1, so we should exclude it. Then this is limit as t tends to 0, and we will rewrite it as t over where is x? Yeah, logarithm with respect to a of t plus 1. And using properties of logarithmic function, we can rewrite it as 1 over, first I'll write it like that, and then I'll rewrite it in that form, 1 over logarithm 1 plus t power 1 over t. Now we know this limit 1 plus t power 1 over t is e, the second remarkable limit. Logarithmic function is continuous, so that is logarithmic of a of e. So we obtain 1 over logarithm a of e, or using properties of logarithms, we can write as natural logarithm of a. And yeah, in fact, that limit which appeared here is very important. Yeah. So, in fact, quite often this is considered as a version of the second remarkable limit. I mean, you see e to the power x minus 1 over x is 1 for a equals to e, right? And also, if we look at this part, then limit as x tends to 0, logarithm 1 plus x over x equals to 1. So these are also versions of the second remarkable limit as well, which appeared during the solution. And for a equals to 1, what we have? If a equals to 1, then a to the power x is equal to 1. So we have the limit 0 over x, and that is 0. So it means that the answer logarithm a is valid also for a equals to 1 without exclusion, any exclusion, right? So, okay, that is concerning that example. Yeah, now there is a lemma for the properties of logarithmic function. I will not prove it because, as I told before, we omit proofs of properties of the exponential function, hence we should omit properties of logarithmic function as well. Okay, now for hyperbolic functions, next example, example 4. Example 4, limit as x tends to 0, sine hyperbolic x over x equals to 1. So, sine hyperbolic, let me recall, what is it? Sine hyperbolic x is, by definition, e to the power x minus e to the power minus x over 2. Cosine hyperbolic is e to the power x plus e to the power minus x over 2. Tan hyperbolic is sine hyperbolic over cosine hyperbolic. And cotan hyperbolic is cosine hyperbolic over sine hyperbolic. Yeah, so, yeah, in fact, also there are secant hyperbolic 1 over cosine hyperbolic and cosecant 1 over sine hyperbolic. Here is the list of hyperbolic functions. Some okay, so what we can do now, we'll write limit sine hyperbolic x over x equals to limit e to the power x minus e to the power minus x over x, and here we can add and subtract 1. Now both limits exist. E to the power x minus 1 over x equals to 1, that tends to 1. We have this observation in the former example, And here, okay, how we can proceed? E to the power minus x minus 1 over x. We can denote minus x as t, then this is minus limit, and t tends to 0 as well, e to the power t minus 1 over t, and that is again, I forget about 2 right here, 2. So that is 1/2 then, yeah. And here we have then minus 1, right? So this tends to minus 1/2, and if we substitute both values, we have precisely 1 as it should be, right? As it should be. Okay, no questions, everything is clear. And that is indeed rather simple. Yeah, example 5 is about tan hyperbolic. So, example 5 is so that limit as x tends to 0 tan hyperbolic x over x equals to 1. Okay. Oops. It's bad, completely bad. Okay, so what we have here, limit as x tends to 0, sine hyperbolic x over x times cosine hyperbolic x, and that is limit as x tends to 0 sine hyperbolic x over x times limit 1 over cosine hyperbolic x. And then, okay, if you look at cosine hyperbolic, because of continuity of exponent, cosine hyperbolic is also continuous, and cosine hyperbolic of 0 is 1. So both limits are equal to 1. That is the solution. Okay. Next example, example 6. Find the limit x tends to infinity, x plus 2 over x plus 1 power x. Yeah. Again, I should say that people who will write like it is written in your lecture notes, that is completely wrong, completely wrong. So, what is written in your lecture notes? X plus 1 over x plus 1 and then it is written like limit x tends to infinity 1 plus 1 over x plus 1 power x. Then it is written limit x tends to infinity 1 plus 1 over x plus 1 power x plus 1 times x over x plus 1. Then it is written 1 plus 1 over x plus 1 power x plus 1 power x over x plus 1. And then it is written, well, that is, never write it like that. Why never write it like that, right? Never write it like that. Because why I cannot write like limit as x tends to 0, 1 plus x power 1 over x. In the same way, look, take a limit in the brackets, firstly, right? That is 1. What is difference between logic of those writings? No difference. And that is completely wrong, right? That is completely wrong. So, of course, quite often people, I mean, when you think about solution, that is a good way. And in fact, everybody thinks like that. But when you write down the solution, never write it like that. So the best way is to use limit as x tends to infinity e to the power x over x plus 1 times logarithm of those brackets. And then everything is okay. So this tends to e, right? Logarithmic is continuous function, so logarithmic of e is 1. That fraction tends to 1, so exponent is also continuous, so we have e to the power 1 times 1. That is correct writing. Otherwise, if you accept, you will make many mistakes in such a way. So don't separate the process of limit into several parts. Otherwise, it may be very dangerous if you consider a huge example and you proceed like that. So let's take firstly that limit and then other limits. So look, this is correct. Why? We consider those two examples, those two limits separately. Why? Because we use the theorem about product of limits, right? So, and in fact, this writing is a little bit conditional. I mean, this is valid because of that. Both limits exist and they are finite. That is why, if both limits exist and they are both finite, right? Then this is indeed correct, right? So this writing is in some sense conditional. From the beginning you don't know, right, if it's indeed both limits exist. But then you check, both exist, right? then the theorem can be applied, so everything is okay. Quite often, for example, if here you have 0 and here you have infinity, right? Then that is wrong. So, okay. Next example. Next example. Example 7. Example 7. Example 7. Find the limit as x tends to infinity 1 plus 1 over x squared power x. Okay, we follow same logic. 1 plus 1 over x squared power x squared times 1 over x, right? So we represent x as x squared times 1 over x. Then, okay, we know this tends to e, so we'll proceed like limit as x tends to infinity e to the power 1 over x logarithm 1 plus 1 over x squared power x squared. That is 1, because this is e, logarithmic function is continuous, so that is 1, and that is 0, tends to 0, so e to the power 0 exponent is continuous, so that is 1. Okay. Next example, example 8. Find the limit x tends to infinity 5x minus 2 over 2x plus 1 power 2x minus 1. Okay, so I will proceed here. Yeah, in fact, we can. Okay, let's proceed in same way as before. Doesn't matter. So, okay, let's have a break. After that, we'll solve it. So. Let's proceed as before. We'll rewrite it as e to the power 2x minus 1 times the logarithm 5x minus 2 over 2x plus 1. Then the limit as x tends to infinity 5x minus 2 over 2x plus 1 is equal to the limit x tends to infinity 5 minus 2 over x over 2 plus 1 over x, and that is equal to 5 over 2. So what we have then the limit as x tends to infinity to x minus 1 times logarithm 5x minus 2 over 2x plus 1, and that is so here we have logarithm of 5 over 2, that is a positive number, x tends to plus infinity, so we have plus infinity again, and the limit of exponent, if the exponent tends to plus infinity, is plus infinity as well, right? So the answer is infinity. The answer is infinity. Okay. Great. Finally, continuity. Poof. Okay, let me write down the lemma. So, lemma, if limit as x tends to x naught u of x equals to a greater than 0, and limit as x tends to x naught v of x equals to b real, then limit as x tends to x naught u of x power v of x equals to a to the power b. After that lemma, some of writings of that form become correct, right? Because now look how we can proceed. For example, now we can compute limit, so proof. Limit as x tends to x naught u of x power v of x, we can rewrite as limit x tends to x naught e to the power v of x times logarithm u of x. Now, logarithm of u of x, logarithm is continuous. If u of x tends to a is positive, then logarithm u of x tends to logarithm a, real number. V of x tends to b. So, because of continuity of exponent, we have e to the power b times logarithm a, or same as e to the power b. So after that, you can use now, so what I say is forbidden, right? So not here, but okay, for example, here you can proceed like that. Yeah, at that moment, right? Here you can use now that lemma in example 7. You have u of x is 1 plus 1 over x squared power x squared tends to e, which is positive, right? And v of x is 1 over x tends to 0, what is a real number. So then no problem after that. After that lemma we can use this writing I mean in a separate way. So firstly you can substitute a and after that b. But again I would prefer to avoid, because yeah, you see, very dangerous thing is here, right? So yeah, okay. Yeah, and concerning this case, if we have 1 power infinity, this case, right? Then here, very useful corollary. And that is another way to avoid logarithmic. Okay, maybe firstly I'll proceed. So let limit as x tends to x naught u of x is 1, limit x tends to x naught v of x tends to infinity, right? Maybe minus or minus infinity. Then how we can proceed? Look, with this limit u of x power v of x. Then we cannot, and of course we cannot write like we did before. Okay, here we have 1. Yeah, that is wrong. That is wrong, right? But how we can do? We can write like that. So e to the power v of x times logarithm u of x, right? Now limit as x tends to x naught logarithm u of x over u of x minus 1. How we can proceed? If we substitute t equals to u of x minus 1, then what we have? We have that limit, t tends to 0 then, right? So if x tends to x naught, then t tends to 0. Then how we can rewrite it? As limit as t tends to 0 logarithm t plus 1 over t, and that is 1 by a form of the second remarkable limit. So how we can proceed then here? Limit as x tends to x naught e to the power v of x times u of x minus 1 times logarithm u of x over u of x minus 1. It means that that is equal to the limit x tends to x naught e to the power v of x u of x minus 1, yeah, once this limit exists. And that is a corollary. Let me write it down. So corollary. If limit as x tends to x naught u of x equals to 1, limit x tends to x naught v of x equals to infinity, and limit x tends to x naught e to the power v of x times u of x minus 1 equals to, let's say, a, and now a can be not necessarily a real number, it may be plus or minus infinity, doesn't matter. Then limit as x tends to x naught u of x power v of x equals to a. There is only one exclusion. Yeah. We should also suppose, yeah, here, u of x not equals to 1 in a neighborhood of x naught. Otherwise, that is, because here we use the limit of composition, right? And for the limit of composition, there is a condition when you can use it. U of x should be not equals to 1 in a neighborhood. Otherwise, that is different. Yeah. And indeed, it will be wrong, right? Because if u of x equals to 1 in an infinite sequence of points, then for that infinite sequence of points, this is 1. Hence, that is wrong. Okay. That is corollary. Okay. Next example. Oh, number 9. Example 9. Example 9. Find the limit limit x tends to infinity x squared plus 1 over x squared minus 2 power x squared. Okay. So, okay, what we have here, limit, we can use the rule equals to limit x tends to infinity e to the power x squared times x squared plus 1 x squared minus 2 minus 1. Because the function is not equal to 1 precisely. In fact, it's never 1. So, yeah, okay. Let us write it. Limit x tends to infinity, e to the power x squared times 3 over x squared minus 2, right? And that is a limit as x tends to infinity, e to the power 3 over 1 minus 2 over x squared. Now 2 over x squared tends to 0, and we have e to the power 3. Yeah. Okay, next example, 10 now. Example 10. Find the limit as x tends to 0, 1 plus x squared power cotan squared x. Again, we will proceed as limit is equal to the limit x tends to 0, e to the power cotan squared x times x squared, and we'll rewrite it as limit x tends to 0, e to the power x squared over sine squared x times cosine squared x. Here we use the first remarkable limit, tends to 1. Cosine is continuous, so this tends to 1 as well, and the answer is 1 then, right? Yeah. Next example. Sorry? Sorry? Once again. Which logarithm? Why logarithm? Rule. Use this rule, no logarithm. That is the essence of this corollary. Okay. Okay. Which we considered. Okay, example 11 now. Example 11. Find the limit. Limit x tends to 1. 1 plus sine pi x power cotan pi x. Okay. Again, we'll proceed in the same way. So that is the limit x tends to 1 e to the power cotan pi x times sine pi x. So cotan times sine, that is precisely x tends to 1 e to the power cosine pi over pi x, right? And cosine pi is minus 1, so we have e to the power minus 1. E to the power minus 1. Yeah, but don't forget to check all conditions, including those, right? So here we have the limit is 1 and the function sine pi x is not equal to 1 in the neighborhood, right? Yeah. Then, what is next? What is next? Okay. Okay. Next example, example 12. Example 12. Find the limit as x tends to 0, 1 plus tan x over 1 plus sine x power 1 over sine x. Again, as x tends to 0, the limit is equal to 1, so we can use same rule. So the limit as x tends to 0 e to the power 1 over sine x times 1 plus tan x 1 plus sine x minus 1. So that is, in fact here we'll use continuity. Why I avoid it in general? Because we cannot exclude infinite limits here, and that is why I would prefer to use in general the form like that, not e to the power of the limit. And that is sine x times 1 plus sine x, and in numerator we have tan x minus sine x, after taking common denominator. After that I can rewrite it as e to the power limit x tends to 0 seconds x minus 1 over 1 plus sine x. Seconds 0 is 1, so we have 0 over 1, that is 0, and that is, hence we get 1, right? Okay, so we completed the list of examples. Let me consider more examples from the standard problem book for our university. More examples. Yeah. Yeah. Okay. So standard examples from our problem book. Okay. Yeah. Example 13. Limit like that. Limit x tends to 0, a to the power x plus 1 plus b to the power x plus 1 over a plus b power 1 over x and a greater than 0, b greater than 0, right? Okay, so we have limit that is equal to, again, if we substitute 0, we have a plus b over a plus b equals to 1, so we have x tends to 0, that is equal to e to the power 1 over x times our base minus 1, right? That is limit x tends to 0, e to the power 1 over x. So we have a plus b, a to the power x plus 1 minus a, plus b to the power x plus 1 minus b. Yeah. So, okay, I can rewrite it as e to the power limit x tends to 0 and a times a to the power x minus 1 over x plus b times b to the power x minus 1 over x times 1 over a plus b. And then what we have, those limits are equal to logarithm of a and logarithm of b correspondingly, so we have e to the power a logarithm a plus b logarithm b over a plus b. That is the answer here. Yeah. Let's consider maybe the last example. Example 14. The limit x tends to infinity, plus infinity of course, logarithm 4 plus 5 e to the power 6x over logarithm 1 plus 2e to the power 3x. Yeah. So here we can proceed like that. Limit x tends to infinity. Let me write like that. Logarithm 5e to the power 6x plus logarithm 1 plus 4 over 5e to the power minus 6x over logarithm 2e to the power 3x plus logarithm 1 plus 1/2 e to the power minus 3x. So what I did, I looked at the expressions and I understand that the second term in this sum tends to plus infinity, so it grows. The first is a constant, hence I would separate this greatest term like that. Then we can use properties of the logarithmic function to write down like 6 logarithm x plus logarithm 5 plus logarithm 1 plus 4 over 5 e to the power minus 6x over, and here 3 logarithm x plus logarithm 2 plus logarithm 1 plus 1/2 e to the power minus 3x. So now you see constant tends to 0, constant tends to 0, and those tends to plus infinity. Hence we divide by greatest term, which tends to infinity, that is logarithm x. So we have logarithm 5 over logarithm x, logarithm 1 plus 4 over 5 e to the power minus 6x over logarithm x over 3 plus logarithm 2 over logarithm x plus logarithm 1 plus 1/2 e to the power minus 3x over logarithm x, and now tends to 0, tends to 0, tends to 0, tends to 0, and we use limits of the sum and of the ratio to deduce that the limit equals to 6 over 3, and that is 2. Right? Okay, we have 1 minute and no connection, right? No connection? Okay, let's stop then.